Hello, and welcome to the video accompanying Chapter 18 on the topic of the stars, a celestial census. What does that mean? It means we're going to be taking a census of the stars, like a census of the population of the United States. This is a census of the population of stars. And a census means you're gathering information about those stars. All right? So that's what this chapter is all about, gathering information about stars. Now you might say, well, in chapter 17, weren't we gathering information about stars? Didn't we establish the idea of apparent magnitude and apparent brightness? Didn't we establish the idea of spectral type and temperature? And lastly, didn't we establish the idea of spectral lines and particular elements that correspond to spectral types of stars? Well, yeah, we have, okay? But we weren't there yet. We're missing a piece of the puzzle. We're missing the information that allows us to really establish the key figure that defines all of stellar astronomy. And by key figure, I mean something that's comparable to the periodic table for chemists. A collection of ideas that's so comprehensive that it is the number one reference. All right? Because chemists, they look at the periodic table, it has everything really you need to know about elements and how elements are related to each other. Right? Even information about isotopes, all these details. Okay? Number of neutrons, protons, atomic mass, so much to know. Well, we're going to come up with the same sort of document for astronomy, and it's called the HR diagram. And it's going to allow us to talk about stars, like in this figure, in a very detailed way. And it has two axes, but it also has more information because it's a figure with two axes, a vertical and a horizontal. But it has more information embedded in it than just those two axes. And an interesting thing is we're actually going to have a dangling bit of information that we're going to have to wait till the next chapter to resolve. But I'll talk about that in just a minute. Okay? So we're looking at another image, and this one could have been in the last chapter, kind of saying, like, oh, look at stars. There's a bunch of different types. There's hot blue ones and colder red ones. Some are brighter than other ones. Okay? So a large variety of sizes, large variety of masses, temperatures, and so on. Okay? And again, we know the temperature based on the spectrum. Okay? Whether it's more blue or more red. Okay? So that's fine, right? That we can say, oh, there's a large variety of stars. But one thing we're going to do here is we're going to specifically talk about some other formulas that relate the types of stars. And we're going to introduce something called luminosity, okay? Which actually is going to dovetail exactly into that dangling idea, which is the main topic of the next chapter, okay? But again, more on that in a minute. All right. But the first thing we want to establish, before we kind of jump into the HR diagram and start establishing the couple formulas you need for this chapter, the first thing we want to talk about is commonality, all right? And so just what's the frequency of certain types of stars? Because the idea here, the purpose of this figure is to imagine if we could be 30 light years away from where we currently are, all right, and look at our little section of our arm of the Milky Way galaxy, our little cluster of stars, right, a tiny, tiny subsection of those 100 billion stars that make up the whole galaxy, what would be kind of the distribution of the stars? Well, many of them would be brown dwarfs, and the brown dwarfs are represented either by a red circle or a blue circle, depending on which study found them, and the caption of the figure explains that. There would also be quite a bit of red stars, so those would be type M stars, all right? And let's see, yeah, brown dwarfs, yep. I was just making sure that there was no white dwarfs shown in this figure, and there's not, okay. So anyway, moving on. So quite a few brown dwarfs. Not the most frequent, right? Because if you look at the circles, in fact, I want you to think about it. If we look at this figure, what is definitely the most frequent thing you see? Oh, it's the little red dots. Okay, so the red dots are the M-type stars. They're true stars, unlike brown dwarfs, but they're incredibly common. They're small, quite a bit smaller than our type of star, which is a G-type star, and you can see there's tons of them. In fact, for every really big, bright A-type blue star, there's about 50 of the M-type cooler red stars. So it's 50 times more common. That's much more common to find the M-type stars. What about our sun? where our sun falls kind of in the middle, being a G-type star. So really there's, even for a G-type star like ours, there's going to be 5 or 6 M-type stars. They're little red ones, right? So then, definitely way more common. And this picture totally supports that idea, right? See, look, like this star here is actually brighter and hotter than our sun, right? So this would be an example of a even less common type of star, right? If you look at ours are kind of the little white dot category. Like that would be one like our sun, that would be one like our sun, right? These yellow ones are a little bit cooler, right? But these ones with the big halos around them are hotter and brighter, right? So you can see there's a large variety. Now there's some you might want to be, you might say, oh, well, this one's red but kind of has a halo around it. Why is that? Probably because it's really big, high luminosity, but still red. How's that possible? Well, we'll get into that because it turns out there are stars that break the rules, okay? All right, but this is the idea. Definitely much more common to have the cooler type stars. Maybe the biggest thing to remember is that M-type are most common by far, okay? No, I'm going to say most right, common. All right, are most common. All right, so another thing we're going to talk about a bit in this chapter as kind of I would say sort of a side narrative to introducing the HR diagram is the idea of binary star systems. Why? Well, because first of all, half of stars in the galaxy exist in binary star systems, or more than binary, so maybe 3 stars that orbit each other. And by the way, a binary star system is just a term given to a solar system that has 2 stars that orbit each other. Okay, our solar system is not like that. There's only a single star. Okay, and again, Jupiter is nowhere close to being a brown dwarf. It wouldn't count at all. Okay, so there we have this idea that there's a lot of 2-star systems out there. And the reason we're going to be talking about those is because by talking about binary star systems, we can discuss some of the techniques that astronomers use for investigating them, and in doing so, kind of shed some light on how we're getting this data. Because it shouldn't just be a mystery. It shouldn't just be like, oh, astronomers collect data, here it is, memorize it. Let's think about where it comes from. And furthermore, the last kind of interesting thing about talking about binary star systems is many of the techniques that we use for evaluating binary star systems, when refined with modern technology, can be used to discover and quantify planets around other stars, which obviously are harder to detect. They're much less bright, they're much smaller mass, but that's amazing, right? And that has led to this revolution of discovering extrasolar planets, which we'll discuss in a later chapter, okay? Because that's really at the forefront of modern astronomy, okay? Now, here's a cool thing. Our closest neighbor, the closest star system to our solar system, is a star system of 3 stars. So just showcasing how common they are, okay? So the two of the stars that make up our closest neighbor are Alpha, let's see, we have Alpha Centauri, A and B, okay? So here their names are, Alpha Centauri, A and B. And they're very close together. They're relatively bright stars, okay? And they show up here as kind of one big spot of light. With the right filters, we can identify that there are 2 separate sources that create that big bright spot of light, okay? And so that might seem like that's it. That's the binary star system. But it's actually not, okay? There is a 3rd star in that binary star system that's much further out. It's sort of orbiting at the very fringes of the solar system, star system, whatever you want to call it. Those are interchangeable terms, solar system, star system. And way out, on the edges, it'd be like thinking about like a star that was orbiting, way past Neptune in our own solar system, on the very, very fringes. You can see it here show up in the figure just barely as a little arrow. And if we zoom in on that arrow, we can see that this little dot, which barely shows up as anything compared to just the background of other stars, is actually part of that system. And it is an M-type star. So it's not even a brown dwarf, it's a true star. And that's that's Proxima Centauri. All right? So you got Alpha Centauri A and B and Proxima Centauri. All right? And Proxima Centauri is technically the closest because it's on the edge. All right? And so it's closer to us based on the orientation of our solar systems. Okay? So yeah, that is our closest neighbor, sort of showcased here, clearly seeing different dots in space as we look through a telescope at this star. Okay? So another example of a binary star system is this one here. All right. This is the revolution of two stars. One of them is a brown dwarf, and the other is an L dwarf. Right. So these are very, very dim stars. But what is special about these, kind of what has happened due to direct observation of these stars, is we can see them revolving around each other in a nice way. So that really, there's nothing special about these stars. There's dim, very garden variety stars, but we're seeing them orbit each other. We're seeing them rotate, and you can see over time that their orbit is such that they sort of spin about each other, like two people dancing and rotating around. Okay, and so we clearly have that dancing rotation of the stars, and one of them we can kind of consider at the middle, but that's just a perspective. That's just saying, okay, well, let's just put one at the middle and kind of hold it as a fixed point, and then observe the other one rotating around. But in reality, they are rotating around their own center of mass, which is this idea here. Okay, that in the case of the previous example, they're both low mass stars, but one is definitely more massive than the other, and so then there's some center of mass that actually really isn't in either star. The center of mass is just somewhere between the two stars, and then so the stars are dancing around that point. This is the actual center of rotation. Okay, and if one star is way more massive than the other, then the center of rotation could actually be within one of the stars. Or if you think about our own solar system, and you think about the biggest body in our solar system, Jupiter. Well, Jupiter is massive, again, nowhere near star mass, but it's certainly much, much bigger than Earth or the other terrestrial planets. And if we look at the center of mass between the Sun and Jupiter, that center of mass is pretty close to the surface of the Sun. All right? So it's actually, it has significantly shifted from the centroid of the Sun up to almost its surface, right? To its fiery hot surface. Okay? So that's the idea about that balance point, that center of mass. And it's illustrated here in a very physical sense. Like you would imagine a teeter-totter, and just putting a fulcrum and a long board and imagining the stars balancing. Because that's what's happening physically. It is a balance of gravitational forces. Okay? So, and that certainly applied to this binary system of these two stars dancing about a certain point, a fixed point. All right? So a further idea about binary stars is that when they orbit around that fixed point, the spectrum changes. All right? And so I bring this up because this is kind of a good, I would say, sort of reminder, a good throwback to some material we saw in the previous chapter. Because we talked about stellar spectra, and we talked about when stellar spectra could change. Stellar spectra could change when a star was moving towards us, which meant it was blue shifted. Stellar spectra could change when a star was moving away from us, because then it was red shifted. All of the known bandwidths would be shifted in the red direction towards longer wavelengths if stars are moving away. And that blue shift just meant that all those known frequencies, all those known wavelengths were shifted towards the shorter wavelength, which is blue. And those terms, again, blue and red, just mean blue is shorter wavelength, red is longer wavelength. All right? And then we even saw that when a star was spinning really fast, its whole spectrum was kind of stretched out because it was simultaneously red shifted and blue shifted on each side of that rotating object. And thus, it made for a spreading of the spectrum. Well, it turns out if we look at the combined spectrum from a binary star system, we see something that's kind of like a red shift, blue shift, kind of like a rotational spreading. Because we see that when the stars are saying the orientation of figure 1, with one moving towards us and the other moving away from us, then we have a shift towards basically towards the red direction, right? So we have a shifting of the bandwidth, all right? Whereas when both stars are moving perpendicular to our line of sight, as in figure 2, well, now there really isn't a shift, because neither of them is, none of the light that's reaching us is actually being affected by velocity, because both the velocities are perpendicular to the line of sight, right? So there's that perpendicular. And the line of sight would be kind of in this direction, right? And the line of light propagation would be just anti-parallel to that, just coming towards us. So the point is that then in figure 2, or figure 4 for that matter, the shift kind of like, it lines up, right? We're not having an effect where it's being moved to one side or the other. It's kind of coming right into the middle, all right? And we can see, right, the two stars just kind of lay on top of each other. Whereas when one is moving away, so B in this case is shifted towards the red, and A is shifted towards the blue because it's moving towards us. If B is moving towards us, then it gets shifted towards the blue instead of shifted towards the red, and A gets shifted towards the red, see, because now A is moving away, right? But then when they're both moving perpendicular, no adjustment, okay? So it's it really is just highlighting the idea of red shift, blue shift, motion towards or away respectively, but for a binary star system. So 2 points of light that we can analyze or astronomers can analyze, okay? And this is just tracking it over time. Because if you track that motion over time, you can then clearly see the sinusoidal behavior of the orbit. Because again, these stars are orbiting each other, or more accurately, they're orbiting a fixed point, a center of mass, an imaginary fulcrum that's somewhere between the two based on their relative masses. And so then we see that B has a particular sinusoidal orbital pattern, an oscillation, an orbit, right? In terms of time versus radial velocity, and that radial velocity calculated from the redshift of known frequencies of light. And then meanwhile, star A also has a measurable sinusoidal behavior. But the signs, the waves aren't identical to each other, are they? Well, they're not identical, even though, I mean, they're definitely synchronized in that one is, that they're maximum in magnitude at the same points. But, what's not identical about them is their amplitude. Why is their amplitude not identical? Why is it that the radial velocity of star B becomes very large as 110 kilometers per second, whereas the radial velocity of star A maxes out at a mere, let's see if we're going from, 30, right? And then we go up, it really has, I would say, has a delta, has a difference of about 20, right? Why is the difference so small? Well, because it's obviously closer to the center of mass. So that implies that perhaps star A is actually the more massive one, thus it would be moving less, right? Because if star A was really massive, it wouldn't really be moving at all, would it, right? In that case, star B would be truly orbiting around it. So the more massive star moves less, which is common sense, right? Just thinking about motion and inertia and all those ideas, okay? All right, so this is just looking at some brown dwarfs in Orion, just kind of getting into the frequency of brown dwarfs and how there's quite a few of them. But let's get on to kind of the main topic of this chapter, all right? And this is the idea of graphing luminosity against something. Now this graph, I would say, is kind of a precursor to the main idea, but is the first time we're going to introduce one of our two equations, okay? And this is luminosity versus mass. And I say it's a precursor to the main idea because this is not the HR diagram. The only difference is an HR diagram is going to have a horizontal axis of temperature. And of course, if you have temperature, you can also have spectral class, because spectral class and temperature are really two ways of saying the same thing. But I'll reiterate that in just a moment. But this is another very helpful graph, and one where we can actually start talking about a mathematical relationship among a census of stars. See, we're sort of getting to the main topic here. And in this graph of luminosity versus mass, or luminosity on the vertical, mass on the horizontal axis, you might think, oh, well, it's a linear relationship. Look, we got a line. But if you look more carefully at the numerical values on the axes, you see that they don't change at the same rate, right? So luminosity goes from 0 in increments of first to 0.01, then the 1, then 100, then 10,000, then a million, whereas mass seems to take a much more conservative scale of just going 0.2, 0.5, 1, 2, 5, 10, 20, So clearly they're not changing at the same rate, and neither of them is changing at a linear rate. For example, the distance between 0 and 2 on the horizontal axis is about equal to the distance from 2 to 20 on the horizontal axis. So what is that all about? And meanwhile, the steps here seem to be steps of 100, but not as in like adding 100, but multiplying 100. Well, that's because this type of graph is called a log-log graph. And log-log graph just means that it's a logarithmic scale. And a logarithmic scale is the same as saying an exponential scale. All right? And so that means that it's not a linear scale. It's a scale where we're taking a huge change in values and we're graphing that by representing it as multiplication rather than addition on the axes. Okay? And in doing so, we actually have a mathematical relationship between luminosity and mass that says that luminosity is proportional to mass to the 3.9 power. Okay? So this is a straightforward exponential relationship. If you know luminosity, then you can calculate the mass of a star by just taking that mass of the star and raising it to the 3.9th power. Okay? Actually, I guess that would be more if you knew mass, right? If I knew the mass of a star in solar masses, by the way, that's the unit, then solar mass is just the mass of our own star. If you wanted to convert it to kilograms, you would just find out how many kilograms are in one solar mass. In other words, how many kilograms our sun has. And then if you just raise that value to the 3/9 power, and you've got luminosity, okay? But since it's a proportionality, it's not the units. So then you have to convert over to the correct units. In this case, it would be measured in luminosities of the sun. Okay, so here's a minute where I have to then give my big kind of caveat about this chapter. Because what are we doing here, right? We have a graph, it's great, we're taking a census of stars, that was the point. But we're cheating because mass we know. We've certainly spent some time introducing mass, it's measured in kilograms, it's the physical concept of inertia. But what the heck is luminosity? Is luminosity brightness? Is that just another kind of, in everyday language, luminosity and brightness are sort of interchangeable terms. But in physics and astronomy, they are not interchangeable terms. And there's a very important difference between them. And we have to actually wait until the next chapter, until chapter 19, where we're going to explain how luminosity is calculated. At this point, it's a mystery to you as students in the class. You could look ahead, I suppose, but for now I just want you to suspend your disbelief and say, okay, fine, we know luminosity. But I also have to say what it is. What is luminosity? Because it's not exactly brightness. Because again, brightness, apparent brightness, is just how something appears to Earth observers. Very important because we're all on Earth, that's where we do our observing, okay? And then apparent magnitude was just the scale that allows us to compare between apparent brightnesses. But what is luminosity? Well, luminosity is actually a characteristic, and I didn't mention this in passing in the last lecture, but it's a characteristic that is actually intrinsic of the star. It actually tells us something about the physical properties of the star in the same way that temperature does, in the same way that spectral class does. What is that? Well, it's energy per time, okay? It's just watts. It's plain and simple, it's wattage. Okay, so luminosity is watts, and if you heard of watts, you probably heard of it because light bulbs are measured in watts. Like you got your 10 watt LED light bulbs, right? Which used to be your 60 watt tungsten light bulbs. So wattage is power. Power is energy per time. The metric units of power are watts or joules per second. Okay, so joules per second, energy per time. That's it. So it's actually a simple concept if you remember what it is. It's just straight up energy per time. Okay, all right? And we know the luminosity of our own sun for a number of reasons. The main reason is because we know exactly how far away it is from us, because we can bounce radar signals off of it, okay? And then we'll talk more about distances in the next chapter. That's going to be the main topic, okay? But anyway, this is our first mathematical relationship, luminosity and stellar mass. Pretty cool, all right? Definitely expect a homework problem on that topic, okay? So, as we're getting into this idea, then let's think about how another way we can sort of measure the effects of a binary star system, right? Because I said we kind of would have the side story of binary star systems. So one is that when a smaller member of a binary star system, so this would be the small star that is effectively orbiting a much larger star, when that star passes in front of the larger star, it decreases the brightness. And again, the brightness would be the apparent brightness that we measure here on Earth, because it's blocking out some of the light. Because the small star, maybe an M-class star, is fundamentally less luminous than its big neighbor, its big, sister orbiting star. And thus, even though it is producing its own light, when it passes in front, the overall brightness is decreased. All right? And then, since the star is, the blue one, is M-class or not, is still a source of light regardless. When it goes behind the big one, the overall effect, the combined light of both stars decreases, but it decreases less, right? So this, so like 4 then corresponds to this smaller decrease by having, some of the light blocked off, and then 2 corresponds to the greater decrease, okay? And actually, I guess that's making the assumption that the smaller blue star is the hotter one. So I actually couldn't remember if the figure was matching up color. And so it is saying that the smaller star is a really bright small star, and then the red one is maybe a big dim red star. Okay? But again, you have, in either case, the eclipsing of either star is going to cause a reduction in the overall light that reaches us on Earth, and bigger reduction when the brighter star is getting eclipsed. Okay? Furthermore, we can look at the angle of the eclipsing to find out the diameter. Because if we know the rate, if we know the velocity, and we might know the velocity from the Doppler effect, okay? So we can, because I mean, you saw in the previous figure, we were able to just observe the stars rotating each other and directly measure through the shift, the red shifts and blue shifts, the actual kilometers per second that those stars are moving through space. Once we have that, and then we find out how long it takes to go from full brightness to eclipsed brightness, which would be this time here, so this measurement in time, well, that measurement in time would then allow us to calculate the diameter of the star. Pretty amazing, right? Because we don't have, our telescopes don't have high enough resolution to actually measure the pixel width of these stars, right? And so instead, we actually can measure their diameter based on their velocity of eclipsing. All right? Okay. So in this idea of sort of taking a census of data, obviously, reference it to the idea of a population census here in the United States, which is, of course, relevant because there's one happening right now. But we can also think of it as a smaller group of people. We could just take the census in our class and compare height and weight. And if we compared height and weight, we would see a clear trend between height and weight. People that were taller would weigh more. People who are less tall would weigh less. And then notice that in this graph, weight gets bigger towards the left and height gets bigger as we move up. And that's kind of atypical because most graphs get larger as you move to the right, and they get smaller as you move towards the left. But in this case, we have weight getting larger as we move to the left because that's actually going to be the same way that the HR diagram is presented. Just kind of by, for historical reasons, that's just the way that it's presented, okay? So I want to sort of establish that way of thinking. So expect the horizontal axis to get bigger towards the left, okay? Maybe word of warning. All right, so we're about to introduce it, but these are the two historical figures that actually created the HR diagram, Hertzsprung and Russell. That's where the HR come from, okay? And these were just, scientists, astronomers in the late 19th century, early 20th century, okay? All right, so here it is. Here's our first time looking at the HR diagram. And this one we're doing for kind of a particular sampling of stars. So maybe some stars that you might know from stargazing, like Rigel or Betelgeuse, our own sun included in there, which you can see is a G-type star with a yellow spectrum, so a yellow peak frequency. And we continue to move on. We got Proxima Centauri, that really dim member of the three-star system. That's our closest neighbor. We've got other stars like Bernard's star, which is known for its huge amount of wandering. We've mentioned that before. Alpha Centauri, another one of our neighbors. And then notice that in addition to some Vega, right, a well-known star for stargazing, as well as Sirius. But in addition to kind of the stars that you might know from stargazing or ones we've talked about in previous chapters, there's also a few other titles here. We see that there's a title here that says main sequence, more on that in just a minute, a title that says white dwarf, and a title that says supergiants, okay? And then on giants for that matter as well. And so when we're talking about these different types of stars, this is going to be something we come back to a lot. The main sequence and everything that's off the main sequence. And by off the main sequence, it's primarily going to be white dwarfs, supergiants, and giants. All right? And that's going to be kind of the way that we try to understand all these ideas, because it's a lot of ideas that we're trying to relate about stars, about stellar lives, about stellar processes, about the two different types of nuclear fusion, all these ideas that we're continue to build on in chapters. But we have now kind of our grounding platform of conceptual ideas here. The idea that there's a main sequence, which I'll explain in some detail, and then things that are off of that main sequence. Okay? All right, well, in addition to having a kind of a HR diagram that just shows a couple of particular stars, we can have one where we have a grouping of many stars. So these are just little dots, they're not named, but this is just kind of this is the census, right? This is just taking a big population of stars and finding out where they fall on a graph of, now let's identify our axes here, of luminosity on the vertical axis and surface temperature on the horizontal axis. And notice that surface temperature is largest on the left at 25,000 Kelvin and smallest on the right at 3,000 Kelvin. Okay? And so that's our graph. That is how we group stars together. And the idea of grouping stars together by temperature, we saw that before, right? We already knew that 25,000 degree stars were considered spectral type O. But what we didn't know before was that spectral type O stars corresponded to luminosities of somewhere between 10 to the 4 and 10 to the 6 times the luminosity of our sun, which in other words means that these really hot type O stars are 10,000 to 1 million times more bright than our sun. And by bright, I mean true brightness, actually joules per second, right? So they're outputting 10,000 to 1 million times more energy per second than our sun. So, a huge difference. There's no way our planet could survive with that much energy if we were orbiting a star like that, okay? All right, so here we have, right? So we have a minority of stars found in the upper right? These are both cool and bright, so things like supergiants and red giants. And then we have a minority of stars in the lower left that are hot but not luminous, okay? So it turns out that these types of stars, white dwarfs, red giants, and supergiants, these are all stars that are either dying, their fusion processes are ceasing to operate correctly, the internal thermostat of these stars is breaking down. In the case of red giants and supergiants, they're on their way to blowing up. Or in the case of white dwarfs, they're the leftover remnants of a star that have already blown up, okay? And so basically you can think of the main sequence as stars that are in the prime of their life, and everything off of the main sequence is either dying stars or dead stars, okay? And so that's kind of a neat way to think about really what the HR diagram is telling us in broad strokes, all right? So this is going to segue to one of kind of our last topics of talking about how we can relate this is a good time to bring it up, but how we can relate temperature to something called energy flux, okay? And actually, before I move on, before I really kind of make that relationship between temperature and energy flux, I'm actually going to go a couple slides back, and I'll kind of circle back around to the HR diagram. But let's go back to this one here, all right? And so I want to bring up a formula, and this is in your textbook, and it says that F equals sigma T to the fourth, okay? Temperature, this would be temperature like the horizontal axis on the HR diagram, in order to make this a reasonable segue for us so you can see how the ideas relate together. But what is F? Well, F is flux, okay? And what flux is it is energy per time per area, okay? So, so essentially it's going to be, joules per second per area. So it's watts per area. And when we look at that, the reason that we care about that is because when we see the brightness decrease, then we can actually calculate the surface area of the star by using this formula, okay? And T is just measured in Kelvin. F is just joules per second per area. Area is the surface area of a circle, or actually of a sphere, because we're assuming it's the entire sphere that is absorbing the energy. So area is going to be 4 pi r squared, which is the surface area of the entire sphere, rather than just, the one cross section, because it is, after all, a curved body that's absorbing this energy. So we have to take the whole surface area into account. And so then, if we think about it, then this is then saying then that F is just luminosity per area. Because after all, if flux is joules per second per area, then the joules per second part is just luminosity by definition. I mentioned that before. So it's just luminosity per area. So that means then that we can think of flux as area, or we can actually, better yet, we can think of luminosity as area times flux. Okay? And so that can allow us then to actually, based on the change in flux, to calculate the luminosity. So I bring this up because I wanted to make sure that I mentioned the formula here in the lecture, because I do want you to expect it in the homework as well. This is one of the formula relationships that we can see for this chapter. Okay? All right. So let's see the last couple topics that I want to make sure that we cover real briefly. We are almost done here. All right, so let's go back to the HR diagram, and we'll have plenty of time to dig into the HR diagram more if you're interested in this idea of dying stars and dead stars and want to know more about them. Don't worry, we certainly will talk about them more in future chapters. I basically just want to just kind of mention this amazing figure that points out that some of the supergiants, these very, very luminous but very cold stars, they're huge. So essentially what's happened is the reason they become relatively cold is they've given up some of their energy to become really large. They become very dense, and they're just not as hot anymore. So they lost temperature energy to gain gravitational potential energy in that size, right? And so you can see how big they are. Look at this supergiant. This is Canis Majoris, and look at it compared to the sun, right? The sun is a tiny little dot that doesn't even show up until we zoom in on it. And this is the size of this other star, this supergiant that is nearly at the end of its life cycle. It's about to go supernova. It's about to shed its outer layers of gas and just blow up, leaving either a neutron star or a black hole behind. Not even a white dwarf, right? So white dwarfs are only one type of thing that can be left behind. In fact, white dwarfs are the only type of stellar remnants that show up on the HR diagrams, because these more exotic types of stellar remnants, namely neutron stars and black holes, they're too weird to even show up on the HR diagram. But my point is that these stars, these supergiants, are massive. If we had one in our own solar system, it would be bigger than the orbits of Jupiter and Saturn. It would be that massive. And here's the other idea that about white dwarfs. That white dwarfs, if you recall, let's switch back to the HR diagram real fast. White dwarfs are very hot, but not very luminous. Well, that's because they're just the leftover core of a star. They're quite small, so their luminosity is limited by their size. And furthermore, they primarily produce their light in the ultraviolet spectrum. So here we have an example of two stars, Sirius A and Sirius B. And Sirius A produces a lot of visible light, and Sirius B produces a lot of ultraviolet light. And both these images are not at the same zoom rate. So here I will circle. So if I circle that star, the less luminous star, the white dwarf, is this one here. So it doesn't produce much visible light, but it produces a lot of ultraviolet light. Likewise, for the very bright main sequence star, it produces a lot of visible light, but not very much ultraviolet light. All right, so kind of case in point of these different life cycles and the different types of light that they're producing. All right, so that's it. That's our kind of first introduction to the HR diagram, our first introduction to luminosity. But again, we haven't justified how the heck astronomers measure it. So that's the thing. Right now, we just happen to know it. But it turns out that I'll spend hopefully a good amount of time and clearly explain how we can even know something like true wattage, because we can't just go up there and measure wattage. We can't travel hundreds of light years and measure it directly. So how do we even know such a thing? But of course, it's crucial to knowing it because the HR diagram is built on it. But anyway, but that notwithstanding, we've established what the HR diagram is, what the main sequence is, at least that it's stars in the prime of their life, how that relates to stellar spectra, then the temperatures. We've talked to how more luminous stars are more massive, more luminous stars are bigger, more luminous stars tend to be hotter unless they're red giants or supergiants. All right, so we definitely have some good rules that we can start to establish, and a couple of simple mathematical formulas that you want to be keeping an eye out for on the homework. Okay, well, thank you so much for watching this lecture video. I hope it's been really helpful to tell you kind of what you need to pay attention to this week, and I will talk to you all soon.
Yeah, you can play.